This last very easy concept in the equilibrium chapter is called the equilibrium constant. And if you have our famous Haber process, as you see here, you might want to know which way does the reaction run and how can you influence that. Well, chemists don't like to say shifts to the right, favoring products, or shifts to the left. Chemists want an actual number, and what we'll show you in this vodcast is how easy it is to calculate the equilibrium constant and what does it mean. So the way a reaction run can depend upon the initial concentrations of either reactants or products. But if you don't change the temperature, what you will find is that when the system reaches equilibrium, you're going to find that there's a constant number that expresses the ratio of products to reactants. And we can make use of that number. Now, the first part of this PowerPoint talks about how that is derived. You do not need to know this because we did not study rate laws. But you could write a rate law showing how the forward rate is equal to a certain amount. And also you can write a rate law that would show how the reverse reaction would run. You don't need to know what you see in these boxes. But what you do know, without putting numbers in, is that the forward rate equals the reverse rate at equilibrium. The only thing from this slide that I need you to know is that these symbols right here, brackets, stand for molar concentration of. And I'll explain where these little powers come from in the next slide. So if you know that the forward rate equals the reverse rate, you could take these rate laws, which we didn't do, and divide them by each other and come up with a number that never changes. And that's called the equilibrium constant. On this slide, this is the value that I need you to know, the symbol and its definition. That stands for equilibrium constant. And it's very easy to set up and to calculate, and the size of the equilibrium constant with a quick glance will tell you which side, reactants or products, is favored at equilibrium. So how do you write those? Well, they're very easy. You put the products in brackets to show molar concentration of on top, and you'll put the reactants on the bottom. If they were gases, by the way, you can also use partial pressure instead of molarity. Now let's take a look at the bottom here. Notice it's the multiply the both products times by each other, their concentrations. There's only one NH3 up here on the top because this is the products, at the top, and there's only one of them. There's two reactants, and so we multiply the concentration of two reactants times by each other. And let's take a look at where those powers of 2 and 3 come from. In the general equation that you see here, the little letters A, B, C, and D stand for coefficients. So in our Haber process, there was a big number 2 in front of the NH3 and a big number 3 in front of the H2. So those become powers or exponents in the equilibrium expression. So if you have capital letters A, B, C, and D standing for reactants and products, to write a general expression for the equilibrium constant, you'll have C times D, remember we always go backwards, products over reactants, divided by A times B, but you'll put those in brackets to show molar concentration of, and you'll raise them to the power they had in the balanced equation. And that's why there's little letters A and B and C and D to the upper right of these guys. So what this looks like at first is that it's pretty tough, but it's so dead simple and you're going to like it. So let's take a look at how you could do an actual problem here. 1 mole of hydrogen iodide gets heated. They specify the temperature because that is the only thing that can change the equilibrium constant, so you get to assume it stays at 510 degrees. They tell you that there is 0.14 moles of each of the products, hydrogen gas, and that should say iodine gas. They're all gases. Calculate the KEQ. First thing you start with is a balanced equation. And by the way, we don't really like using this double-headed arrow thing, but somebody please find us a reversible reaction arrow set on the symbols and let me have a copy. Now, H2 and I2 are Brinkelhoff or diatomic gases, so I first have to balance the equation. Okay, now let's take a look at what you do next. You write the expression. So the KEQ would be equal to the hydrogen times the iodine concentration divided by hydrogen iodide squared. Here are the initial concentrations that were given to you. So you write the expression, then you substitute in the numbers. And we like this problem because the 1 squared makes your math very simple. 0.14 times 0.14 equals 0.020, 2 sig figs, because the number 0.14 has 2 sig figs. So what? So I got this number. What do I do with it? The size of the equilibrium constant tells you at equilibrium which one is favored. So favored means you're driving to that side. So if you did a KEQ and you got a number larger than 1, that means the number in the numerator must have been larger than the number in the denominator. Products must have dominated the equilibrium position. So if you get a number greater than 1, you know products are favored. If the number turns out to be smaller than 1, that means that the reactants must have had greater concentration, since they're in the denominator, than the products on the numerator. That means, according to this picture, you must be favoring the reverse reaction. You would be going from right to left. The cool part, though, about writing these equilibrium expressions is that if any of the reactants or products are solids or liquids, you totally get to ignore them. They become 1 in our equilibrium constant expression. So what I'd like to do is have you reach for a worksheet that looks something like this. I'll work through a couple of problems with you, and then your goal will be to complete the equilibrium worksheet on your own, check some answers, and or turn them in for grading. So find that worksheet, and now let's jump down and show how you write the expression in the first place. Go down to question number 3A. It says 2A gas plus B yields A2B gas. So they're all gases. I have to include all of them in the expression. We always do products over reactants. We place them in brackets, and the only thing that's different here is my concentration of A2B, the product, being divided by the concentration of A times the concentration of B, but the A is squared because there's a coefficient there. It's just that simple. In the next part of this problem, you'll be given the values to substitute in and calculate the KEQ. Let's look at another example. Now there's a lot of writing here, so just look at the top part for the moment. Write an equilibrium expression for the following reaction. So you might have written A2B over A2 times B with brackets around them. But B is a solid. And whenever you have a solid or a liquid, you may assume that their concentration is so great compared to the concentrations of gases or solutions that they don't change, that they're essentially constant themselves. So the rule is, if you see a solid or you see the symbol liquid, it becomes 1 in the expression, and you just ignore it. So that's why this expression is simply A2B concentration divided by A2 concentration. Let's follow this problem through to its completion. Now that you have the expression, you substitute in the values for A2 and A2B. A2B is 1.4 times 10 to the minus 5. A2 is 1.9 times 10 to the minus 3. This is the number that falls out of my calculator. I threw in a few digits to show you. You would have needed to round this off to 2 significant figures because the number 1.4 and 1.9 have 2 significant digits. Finally, the second or last part of these questions say, who is favored at equilibrium? All you have to do is look at the magnitude of the number. If it's less than 1, that means the left or the reverse reaction must be being favored. Reactants are favored at equilibrium. And if the number had come up greater than 1, products are favored at equilibrium. Hopefully, you'll be masters of KEQ when you finish the rest of that worksheet. Until next time.